I run the Metaswitch networking business unit, but within Metaswitch we have this open source project called Project Calico, and the way we've set this up is very much kind of community oriented, and everyone in the project is an evangelist, so that's what we're doing out here tonight. Metaswitch is a Sequoia-backed company, but not perhaps the typical Sequoia capital startup. We've been around for 30 years. We've got 1,000+ global customers, kind of established and profitable. But within that kind of established company, we've set up Project Calico really very much as a startup and working at the same kind of speed that you see guys like Mesosphere working at, and we're very much part of that community. We're Project Calico within Metaswitch. It is, we say, sponsored by Metaswitch. Right now, the engineering team is pretty much all comes out of our organization, but we're increasingly doing a lot of integration where folks from the orchestration companies, from other organizations around the ecosystem are contributing and are putting stuff back into the community. So. If you like what you see, download, you want to get involved, we're absolutely open to people contributing. What we're going to talk about is what we call a pure layer 3 cloud networking solution. So I think one of the things we really commonly hear about Docker and the challenges that people have getting it working is, how the hell do I get my applications talking to the outside world in a consistent, manageable way? So we'll talk about how you do that. But it's not just a solution for Docker. One of the other things we hear from folks is, hey, I'm standing up an OpenStack data center with a bunch of virtual machines. I'm also doing something with some containers, maybe orchestrated by something like Marathon, and I've got bare metal servers, and these need to be integrated somehow, and how do I have a consistent networking layer across all of these? So we kind of have that bigger picture in mind as well. So, let me get here. So, just to step back and try and think about the networking solutions out there for Docker today. There's really, you can put them into two main camps, and the first one is what comes with Docker out of the box. It's very simple. Essentially port forwarding or port mapping. Basically the same kind of technology as NAT, network address translation, which there's a reason why it's there in the box and what is done by default, because it works, it's simple, it's easy to understand what's going on. But you will find, and people do find, that it breaks in scale, it breaks in all sorts of ways, it breaks certain applications. If you have multiple applications which all need to listen on the same port, then there's it's not obvious how you manage the mapping to the external ports and the internal ports. So we definitely hear that this is a consistent headache that people have. So moving on from that, people have looked at what's the solution for this. Well, let me give each container its own IP address, then it can do whatever it wants with its ports inside that IP address. And the typical way this is done is with what's called an overlay network, where you're essentially making a private addressing space and running encapsulated over the underlying real network. So you'll see technologies like GRE tunnels, maybe MPLS, VXLAN being talked about here, maybe some more proprietary encapsulation techniques, but they all have in common that you're taking this IP address or IP packet and encapsulating it inside some outer wrapper. I'm going to talk for a couple of minutes about why we think that's bad, and then we'll talk about Calico. It really is kind of the sweet spot between these two that gives you the advantages of real IP addressing, but the nice understandability and very kind of simple nature of port forwarding. So let's think about virtual networking and how this works. So the way this typically is implemented today is people implement a software-based vSwitch in each node. So typically open vSwitch, but there are commercial version, commercial alternatives. And I'm not sure if you can see the colors here. I have purple workloads and green workloads. And the idea here is that the purples are meant to be able to talk to each other, the greens are meant to be able to talk to each other, but the policy is you don't want purples to talk to greens. So you'll typically set up a layer 2 segment with for each of those kind of tenants or security groups. And when they talk to each other, then it's fairly straightforward. It goes through the vSwitch, which is the piece of software which is going to add the encapsulation headers on. If you've got broadcast, then it's going to flood those out across the network, and that's how that works for both blue and green, purple and green. The challenge comes if you want to break out of this world, right? So that's fine if you're working just within this private IP addressing domain. But if you want to get into the real world, or if you want to break between them, so you want purple to talk to green, then you have to stand up separate instances, separate applications, which are essentially forwarders doing translation between these domains. So essentially soft routers on top of these switches. If you want to get a public IP address allocated, this is a little bit like when on Amazon you request a floating IP. You're essentially setting up a NAT service, which is converting the external public IP into some internal IP. Similarly, if you've got devices in your network that are bare metal or network-attached storage or something like that that just has a public, effectively an IP that's not managed within this virtual domain, you need what's called an on or off ramp, essentially typically a router to do that. So we think there's all sorts of issues with doing this, not least the complexity of management, the complexity of setting these things up, the overhead, and actually to a large extent the diagnosability. When stuff goes wrong, it goes wrong in a bad way because it's not obvious to you as the application developer how your packets are getting routed, how what you're seeing in terms of the IP messages that are flowing translates into what's actually going on the wire. So these are fundamental issues with the overlay model. You just can't get around them. And when you start talking about containers as opposed to VMs, and you're getting hundreds of these things on a server living for seconds rather than hours, then it's a very much more dynamic environment, and these issues just get complicated even further. So if you take a step back and think about what are you really trying to do here, it's really quite simple actually, and it comes down to I've got a bunch of workloads, each of which, natively everyone's applications these days want to talk IP. That's what you're writing for. You're not doing any strange things with layer 2. So I want to be able to get my IP packets out. We want to be able to communicate with one another and to the outside world. And I have some kind of policy that I want to impose as well. So I want to be able to say, this set of applications can talk to this set of applications but can't talk to some other set for some particular set of protocols or whatever. So you need some kind of policy enforced. And if you think about the way virtual networking has worked, they've combined those two concepts of how do I get from A to B with am I allowed to get from A to B, because whatever's in a single domain, a single layer 2 domain, is allowed to talk to one another as if they're plugged into a single switch. And if they're not in that same domain, they can't talk to one another. And if you want any more complex policy than that, you then have to stand up a separate firewall service, which adds another layer of routing and complexity. So we took a step back and said, if you think about these requirements, we've built a network before which implements them, and it's called the public internet. It scales pretty well to more than a few million endpoints last time we checked, and let's just apply these same principles. So, very simplistic terms, this is how the internet is built. You have a bunch of endpoints talking IP to routers which communicate via BGP. So we said let's put those endpoints and their first router, their first hop router within an individual compute node. So those could be virtual machines, they could be containers. That virtual router will come onto how we implement that, but it's very simple. And then running over any kind of fabric that can transport IP. So that's what we've done. So there's three aspects to implementing a solution like this. So the first is distributing information about which IP address is located where and how do I reach it. So we use BGP for that. That's a proven protocol. Has the advantage that not only does it work within the Calico cloud, but when you plug an edge border router onto your data center, then it can just talk with that natively. You have a data plane, so you've got actual payload packets going around the network. How do you forward those? So we're using the Linux kernel for that. There's no vSwitch in the picture here. And then you have to impose policy. And we do that we have a data model that is pretty flexible, basically maps to Linux access control lists, Linux ACLs, and distribute those using etcd. And that's just essentially implements a local firewall on each compute node. But we've used techniques such as using IP sets within the Linux kernel that allow that to scale pretty well. So the architecture here is, I'm kind of drilling in the next level from this, is whatever the orchestration system is. So that could be Mesosphere, Marathon, or could be Docker Swarm, or OpenStack, and anything which is managing the workloads, and that's the layer which knows that a workload has been created. I've given it this IP address, and those are increasingly having open plugin APIs. So we plug into that. We have an agent which runs on each compute node, which programs information about a new workload that's been created on this machine into the routing table in the Linux kernel, programs policy into the ACLs, into the Linux kernel ACL table, and then all the packets coming in and out of that machine go through that routing table and ACL table. So we're using a lot of existing open source projects here. So for the BGP stack, we're using Bird, which is actually the most widely deployed BGP stack in European internet exchange providers. So it's deployed at scale in real networks, running a good chunk of the internet. We're using obviously the Linux kernel, etcd, and whatever the plugin is typically based on open source. So where we're at with this, I'm going to give you a quick demo in a minute of just to give you an idea of what it looks like. We have essentially a trial version available for OpenStack. We're just beating on that with testing, and we think in a couple of months we're going to be ready to say, yeah, this is good to deploy at scale. We have a demonstrator version for Docker, where really the key thing stopping us getting up to that same level as OpenStack is doing the integration with the various orchestration layers. And that is, you can go download, and I'll give you pointers to that as well. And in fact, what I'll do in the demo is just going to show you, walk you through the steps once you click the Get Started on Docker on our website, from literally an empty box to trying it out. So a few other things that may not be obvious from that very quick kind of overview of how we're doing this. The first thing, and you'll see this in the demo, is from a diagnostic perspective, suddenly everything becomes easy, because if I'm within the context of the container or in the context of a VM, I send a packet out, it just gets routed, and I see all of those router hops with IP addresses that I understand. So I do ping, I do traceroute, they work just as I expect. So anyone who's got a very basic understanding of networking is going to be able to tell what's going wrong if something's going wrong. Because I am literally just doing IP routing, I don't have requirements for on or off ramps. I just have to say this workload is allowed to talk to this server. Or if I want a container to have an external IP address, a public IP address, I just assign it a public IP address as well as a private IP address. No issue with that. And then someone asked about load balancing, right? So, and yes, you can put load balance, you can deploy load balancers and things like that. But one of the nice things that just falls out of this model is because I'm doing IP routing, we have techniques within IP for doing load balancing, right? We have anycast, we can have equal cost multipath, and using ECMP and anycast, you can just have multiple workloads all with the same IP address doing load balancing. So there's a lot of things that we've not been able to do because of the impediments we've put in our way. And once we say, no, this is just plain vanilla IP, it just works. So I do encourage you, actually I've got a few postcards if you want to take something and take away a link to remember, but pretty easy to remember, projectcalico.org. If you go on the homepage, you'll see there's a pretty prominent button, Get Started on Docker. You click on that, it's got all the instructions, go play with it. It's up on GitHub, check out the code, and there's a mailing list to get involved with the team, and our team is really responsive in terms of if there are issues or questions or whatever, so don't hesitate to post on that. And there's another meetup tomorrow, so this is an ad for another meetup. There's a downtown NYC tech group, and that's going to be hosted at the Packet offices, and they've got they're doing a real kind of hands-on thing, giving everyone with laptops a chance to try it out, and we're going to have one of our solution architects there giving hands-on tutorials. So that's going to be fun. Looking forward to that. So I'm going to show you. Yeah.
So you mentioned CoreOS.
Yeah.
So can you run typing to the kernel on basic, simple CoreOS?
Yes.
Code,
in fact,
atomic?
I'm going to show you running on CoreOS.
Maybe have some tomorrow for this. Like a CoreOS.
Yeah, I don't know the exact setup, but I know most of what they do, I think, is on CoreOS, so I would assume that is it. So we actually like CoreOS because we're using etcd. CoreOS comes with etcd, so there's, that removes an installation step because it's already there, right? And we're going to stand up 3 containers in them for actual applications, A, B, C, and each node has to have Felix and Bird running, as you saw in the architecture diagram. And then on one of them, just because it's easiest to put it there, we're going to put the master process. But in fact, we've actually moved the architecture to include etcd. You don't have to have that master process running there if you're using etcd. And you'll see when workloads get added and IP addresses get assigned, the Bgp stacks will communicate with one another to ensure that both nodes are aware of what's on either side, and we'll be enforcing the policy rules. So container A and container B, even though they are on the same machine, they're not going to be put in the same security group, so they're not going to be able to send packets to one another. Container A and container C, even though they're on separate machines, because they're in the same security group, they can talk to one another. So hopefully you can see this. Can we maybe put the lights down again like we did last time for the screen? So the first couple of steps here are actually just downloading the code, and we've got a Vagrant file here, which you can. So if you have a machine, the machine here is clean with all it has on it is Git and Vagrant, and that's basically it. So we use Git to pull down the Vagrant file, do Vagrant up. That sets up the 2 virtual machines. So this is effectively just standing up the 2 physical servers. There's no, we're not setting anything off running at this point. So, that is the essentially just pulling down the code. So we've now, in this window, we've SSH'd into the first machine, which is labeled Core 01. So first thing we're going to do, if you look, there's a program that we have in here called Calico Cuttle, and this is essentially a control application that we've created. If you were fully integrated into an orchestration mechanism, you wouldn't need this app, because this essentially takes the place of an orchestrator. So the first thing we've done is invoke Calico Cuttle with master and told it the IP address of the machine that it's running on. So that master node, the first one that I said, is now up and running. The next thing we'll do is pretty straightforward, do the same thing, but say node. So this is setting up the Felix and the BGP containers. You'll see there's a little message comes up there. I'll come back to what that means in a minute. So now you can actually see standard Docker PS. We can see the node and the master are each up and running. Now we go and switch into the core OT2 context, and now we're on that second machine. We'll basically do the same thing within that context. We're going to start just the node because we don't need another master. So this starts the Felix and BGP processes on that node, and we give it the IP address of the machine it's running on. So back to the first machine. So I said I'd come back to that comment there where it says run export Docker host. So we didn't want, if you're familiar with Weave, for example, they wrap the Docker run command. You have to issue Weave run instead of Docker run. We didn't want to do that. We wanted to basically intercept all the Docker API commands. So we use something from Cluster HQ called PowerStrip. If you're familiar, you guys are familiar with that, it allows you to plug in multiple storage or networking elements and keep the existing Docker APIs. So we essentially, what we do is, if you set the Docker host environment variable to be a different port, then it forwards the API commands to us. We can intercept them, and then they're forwarded onto Docker. So you just have to do this once, and then everything just works with a standard Docker command line. So we're going to do Docker run of our container, which we call con A. A little bit of typing issues here. And we set in the command line here an environment variable Calico IP. So that tells Calico what IP address this container should have. And we're going to run, what we're going to run in this is BusyBox. It could run any kind of container. BusyBox happens to have some useful utilities in it. So container A is now running. We'll do the same for container B, but obviously it needs a different IP address. That's now running. Now we're going to go over to the second machine and have to do the same thing with the Docker host environment variable and run container C. And give that its own IP address, which is distinct. So now we're going to do something new, not via the Docker line, which is creating a security group, which we call group 1. And Calico group add group 1 creates that group. Calico group add member group 1 con C puts container C into that group. But we've only got container C in that group right now. So we're going to do the same on the first machine. We're now going to put container A into that group as well. And now we can ping, you can see this is from the container A IP address, so Docker exec con A pinging to the IP address of con C. We can't say con C because con C has no meaning on this machine. It doesn't know about con C, it only knows its IP address. So packets get through with a minimal delay. Now if we try pinging from con A to the IP address of con B, which is the 192.168.1.2, we'll see it doesn't get through, 100% packet loss. Even though they're on the same machine, we haven't installed a security policy that allows A to talk to C. So there's a few nice things that follow from this. Actually, before we do that, I think just to show you within this Calico CUTL app, we have the ability to see which containers are within which groups. You see group 1 has 2 containers. Certainly scope here to do a nicer UI on this. And then the next thing we'll do is look at the routing table on the host. So you'll see, if you remember back to what I said, we're using the Linux kernel. Felix is programming routes into the host. It's programming rules in. So you can see the fact that you can get to 192.168.1.1. That's container A's IP address, and 1.2 is container B's IP address. Are all local taps. 1.3 is an available route. There's an available route for it, but that's going out via the physical Ethernet 1 device because that's on a remote network. And now the really nice thing is that we can actually diagnose what's going on. We can do a trace route just the same as if these were physical devices plugged into a switch. So we're going to do a Docker exec on container A, a trace route to container C, which is the 1.3 address on the second machine. And you'll see our first hop is to the Linux kernel on the first machine, second hop to the Linux kernel on the second machine, and then straight up the next address is the container that we're going to. So that's really what we've been trying to get to. All this complexity to set up is such that we can just ping, trace route, send packets from container A to container C because we've defined the policy that enables us to do that. So that's really kind of the TLDR version here is, you want networking, Calico just does it. It does it the way you think it should work. There's nothing kind of complicated about this, nothing you really have to learn, and it does it with kind of security out of the box in ways that scale up. So that's, yeah.
One more question. So if you forget the containers, you focus on applications. Applications have different components. They may run in one or multiple containers. So if you host the application, you want to set up policies for securing those applications. Calico seems to be a good option to securing the policies focused on applications.
Yeah.
And say who can talk to them, which component can talk to where in which container. Can you set up the policy down to the level of port?
Yes.
Very granularly, so you do 100% breadth around the application of who and what component can talk and everything else not?
Yeah. So the question is essentially how fine-grained does this policy get? And that comes down, so the data model we use essentially is anything you can program as a stateless Linux ACL, you can put into our data model. What I showed here is obviously much coarser grained in that just saying, either you're in a group or you're out of a group, right? And the reason we do that is because there are a lot of orchestrators which work in that way. So, OpenStack being a prime example of that. We expect this to be driven from orchestration systems that could put much more complex security policy into that data structure. And you can just write it to look at our data model. It's a straightforward JSON format, and you just put it into etcd, and we'll pick it up.
So if we have like a OpenStack and multiple funded compute nodes, can export your data model somewhere that we can spawn across all compute nodes?
Yes. So the question is, can you spawn the data model across multiple compute nodes? Yes, because the scope of an etcd cluster, right? So you can have an etcd cluster that's spanning multiple data centers. If you have separate clusters and want to synchronize them, then there's going to be some work involved there, which we've talked about with some. We're talking with some operators who are talking about like 500,000 servers that they want to run this on, and then you get into those kind of questions. Globally distributed 500,000 servers is potentially another question. But for most data centers, you just expand the etcd cluster to everywhere you want it to be.
So I have a complicated two-part question. And with like the software-based networking, is there any reasonable theoretical limit? Because you just mentioned like scaling up, and what sort of hardware requirements for networking hardware would be required to scale up to thousands of machines?
Yeah, good question. So the question is basically, how high does this scale and what are the theoretical limits, right? So At the moment, the testing we've done, we've been limited by the bottleneck has been the orchestrator and how much, how fast it can actually create and how many nodes it can process. We've put, for example, on the ACL side, we've scaled up to like 16 million ACLs, and it has a 0.04% impact on packet throughput. So, we feel pretty comfortable saying that the security side of this will scale up to millions of workloads. BGP is certainly proven to scale up to, hundreds of thousands of routes, right? And remember, each route is essentially each server is connected here is like a router. So, we think it'll definitely go up into the tens or hundreds of thousands of servers with, hundreds of thousands to millions of workloads on them. But we've not yet spent the money on Amazon hosting to prove that.
Is there any consistency issues with using etcd to store these things? Like you have thousands of machines, could there be like race conditions adding entities?
So that theoretically is what etcd guarantees us is consistency. And you actually, you pay a little bit of latency penalty for that consistency. But remember, we're just using etcd for the policy. And one of the nice things about how we do it is we separate out what policy is required to be imposed on each server, such that a server only needs to watch for the policy which is applicable to it, not the entire network. So, if it's only running 20 workloads, then it only needs the rules which are applicable to those workloads' IP addresses. Okay. There's another question at the back. No.
Kubernetes workloads. What's your experience? What's your confidence?
For what kind?
Kubernetes workloads.
Kubernetes workloads. We have, so we've not completed our Kubernetes integration yet. We're about that far away from it. But we pulled the guys off that were doing that to work on some other Mesosphere work. So
when do you expect approximately?
In the next couple of weeks. Yeah. So certainly in the next month. Yeah. Are you working with Kubernetes? Yeah.
It's a nice option, so it would be nice to.
Okay, I know we've got a few other speakers tonight, and time is getting on, so I'll wrap it up there. Please do come and talk to me afterwards if you've got any questions. Okay, thank you.